Hi, so in the previous video, what I did was I solved the cubic equation on the left side using Vietta's formula, and I have the solution already marked there, so it's no surprise. But what I want to do in this video is do the same problem, but using the rational root theorem to find the roots and the factorization. So we'll do that, and I guess the length of the video, we'll look at how long the video is, and maybe we can see which was faster. But I think it's good to know both methods either way, so. Um, let's do this one with the rational root theorem. So what the rational root theorem tells us is that um, basically that all the rational roots will be a ratio of the first term and the last term. And of course, this is the highest degree term and the constant term. It doesn't work to, one thing I thought was a trick sometimes is with the same thing with Vietas is if you just because you have um, the equation arranged differently, it doesn't matter. It's still the constant, the lowest degree of the constant term and the highest degree term. And so what you can do is look at um, the factorization of. I won't worry about the sign right now. So we'll look at the factors of 12 and the factors of 3. So the factors of 3 are just going to be 1 and 3. And the factors of 12 are 1, 2, 3, 4, 6, and 12. And so then all of our rational roots are going to be, let's see, so we're going to have plus, so we're doing this in the numerator and this in the denominator, the three in the denominator. So like 1 over 1 plus or minus 1 over 3. Then we'll go to the 2s. So we'll have plus or minus 2 plus or minus 2 over 3. We'll get a plus or minus 3. We could also get a 1, but we already have 1, so I'm not going to do that again. We'll have plus or minus 4, plus or minus 4 thirds, um, plus or minus 6. 6 over 3 is 2, so we'll skip that because we already have that here. And then last, we'll have plus or minus 12. And then 12 over 3 is 4, but we already have that. So what this is saying, so all the rational roots are going to come from this list. That doesn't mean that you still could have imaginary roots, and then you could have irrational roots. But of course, if that was in this equation, that becomes kind of harder to find. So when I create this, I'm creating this where all the roots are rational roots. So by using this method, we should have all the roots. Then what you can do next is, so it's still a pretty significant list, and you can do guess and check. That's kind of a pain, right? Because there's that's a lot to check. So one thing I do sometimes, you can use real quick Descartes' rule of signs is you can check the sign changes to get a sense of the positives and negatives. So I'm not going into extreme detail, but you just can check. What you do is you check the sign changes. So I think I already said that. So this is a positive, so there's no sign change here, but there's one sign change here, and then that's not changed. So we say there's a possibility of one positive root. I think it actually works. Well, let's just do the next one. So I think we're gonna have one positive root. But then, so for the next, what you do to get the negative roots is you can just plug a -1 in. So like if we plug a -1 in this equation, we'll have a new, I'll rewrite the new polynomial. It's going to look like, but notice when you square -1, nothing happens, doesn't change the sign. So then you just do the same process on this equation. So the sign's going to change once and twice. So this is going to tell us that there could be two negative roots, or it can be 0. What you do is you count backwards but like I don't even know how to explain this. You so it's like if you counted this and you came up with 7, you'd count down by twos for the possibility of the roots, or if it was 6, it would be like that. So that's kind of how I determine there has to be one root, is because you can't deduct 2 and have -1 um, possible roots, because -1 roots doesn't make any sense. So sorry, that's not a very detailed explanation, but I think that's what I think we'll hold with that for now. So we got, I'm suspecting probably 2 negative roots and 1 positive root. So anyway, though, what I usually do to avoid guessing and checking this full list is I go for the easy stuff. Like I'm gonna go for try like 1, 2, maybe avoid the fractions if I can help it. So let's start. I'm gonna rewrite this equation down here just so I get some room to work with. So we'll call this our f of x. Then what I want to do is let's do some checking. So like I think first I'm gonna try. I usually try 1, but I'm actually don't want to get the answer that easy, so I'm gonna stall and go for 2. So plug 2 into this equation. We get 8 times 3 is 24. 2 squared is 40 minus 2 minus 12. And that's not going to be 0. You don't really have to even add it up. You just want to see if it's 0 or not. Let's try -1. Okay, so we get -3 plus 10 plus 1 minus 12. 11 minus 15. No, that's not 0. So then the next thing we'll check is we'll just try 1. Like I said, I would usually try that first, but let's try a 1, and we get 3 plus 10 minus 1 minus 12, and that equals 0. So we found a root, and it's 1. What I'll do from there is, so if we know 1 is a root, then we know we can factor x minus 1 out of our polynomial. And so because I don't like checking all those roots, what I'd like to do is take that and turn this into a quadratic, which is going to be easier to deal with. So you could do polynomial long division. I actually like to do this little, if the equation is not too bad, I like to just do it on the fly. So like I know we have this, I know we have a root of 1. I know we can take out an x minus 1. So I know we're going to have a quadratic. So what I can do is just kind of write the shell of it. And then I look at like, okay, if I know I need to get back to a 3x to the cube, if I know the cube term has a 3 in front of it, I know this has to be a 3, right? Because this is a 1 here. So I've got one term. Then based on that, I know I'm going to be multiplying a -1 times 3x squared. So I'm going to have minus 3x squared, but I want a 10x squared. So this has to be a 13. And then you can just look at your last term, minus 12, to know this has to be a plus 12. So just, I don't know, a little quicker than doing polynomial long division is to kind of just fill in the blanks. And you can kind of double check, like if you were to like, how do I get this minus x term? Well, I got 12x from here, and I got a minus 13x here, and that's going to be minus x. So this is going to work. So then all I need to do is I've got this quadratic now. 3x squared plus 13x plus 12. So I was going to use, normally what I do is like, I mean, okay, if you can clearly see the factorization, you can just play around with it, or you could do Vietta's formula. But I feel like this is a video about rational root theorem, so maybe we could just do rational root theorem again, even though it's going to yield a lot of the same results. So I'll do it really quick. Actually, it's still going to be everything within this list. So what I could do is there's no harm in just like trying more of these things. Let's try like 3. Although, okay, the other thing is these are all positive signs here. So we know we're looking for a negative root now. There's no way to have a positive root, because if I plug in any positive number here, I'm gonna be yeah, I'm gonna be looking at a positive number. So like, okay, let's try like -2. So we're gonna have 12 minus 26 plus 12, and that's not equal to 0. Let's try -4. That's gonna be 48. Just plugging into this again. -52 plus 12. That's not equal to 0. Let's try -3. That's going to be 27 here. -39 plus 12, and that equals 0. Okay, so -3 is a root. So then I can actually just repeat again, like exactly what I did. We already know that we have x minus 1 as a root, but now we know that -3 is a root, so we have x plus 3 can be factored out. And this is just going to be one term now. So this gets real easy at this point because, again, I know that in order to get this quadratic, I have a 3 here, so I know this needs to be a 3. And then if I just look at the constant term, to get a 12, I need this to be a 4. 3 times 4 is 12. And I can just kind of double check, like, okay, if I was to FOIL this out, 9 plus 4 is 13. So actually, that is going to be, so we didn't actually have to find the hardest root, which here is going to be -4/3, right? We kind of got that one just by doing our long division at the end. And we got the same result as we had right here, just in a different order. So yeah, I think that was a little quicker. And I guess even though it's faster, I don't like rational root theorem very much because you usually end up with this big list. And if the roots are not, it could be a bigger list, obviously. And if the answers aren't easy, like a 1 or a 2, you're spending a lot of time checking answers. So it actually can get pretty long if you have to check a lot. But so that's it for this one. You can check out the previous video where I went over the Vieta's formula, and I'll have a link in the description to both. I don't know. I'll have a link in the description to this quiz, and you can check out both videos. Thank you.